Hello, ladies and gentlemen, and welcome to the fifth and final part of these quantitative methods pre-course preparation. In this last topic, we're going to talk about financial mathematics. Now, this is the part that will be useful for you in your jobs, but, and pay a lot of attention to this, is the one that is going to be the most relevant for you as individuals for your own private lives as well. We all take out loans, we all have credit cards, we all have bank accounts, we all have investments if all goes well, and this is the one that, if you don't know, is the one that is going to allow you to learn how to make decisions about not just your company's finances, if you're in that position, but your own finances. What mortgage should I take out? What pension fund should I join? Should I aggregate the pension funds from my various jobs? All of these are questions that you can answer with what we're going to cover in this session. And so it will be important for you both personally and professionally. So bear that in mind. As always, the next few slides, just a reminder, this are a set of notes, and these recordings are both for those of you who have never learned, in this case, financial maths, and want to learn something, at least to start your knowledge on the area that you can develop further with further studies. But it's also for those of you who have learned it, but either have learned it in a different language with different terminology, or have learned it a long time ago and want to refresh your knowledge of it. We've now covered the previous four parts of key mathematical concepts: data exploration, probabilities and probability distributions, and simulation and optimization. And for the next hour and a half, I'll be taking you through financial maths. As always, you have these lecture notes and this recording, but you also have some practice exercises and respective solutions for those exercises. There's also the references, which will not only explain the concepts, but will also include additional practice that you may want to do. So, without further ado, let's start with financial maths, and let's look at number one, what type of questions we can ask ourselves that financial maths concepts are going to help us to answer. Number two, how to do it. So we've got questions like, how much will I earn in terms of interest, in terms of return on my money? How much will an investment I make today be worse? And here you start asking yourself the question, but if I make the investment today, it's only going to be worth something in the future. Well, that's one of the concepts we're going to cover. It's about future value and present value. And we can always equate a future value to a present value. So we can assess any investment, how much it is worth at any point in time, by calculating future or present values. So whenever I make a decision, if you have three investment opportunities, you're going to have to ask ourselves which one is worth more. Now, if one is for 3 years, one is for 5 years, one is for 7 years, you can't compare how much you're going to receive in 3 years, 5 years, and 7 years. You have to compare it at the equivalent amount at the same point in time. So you either check all of them at 3 or all at 5 or all at 7, but technically speaking, those will not happen what will happen is 1 in 3 years time, 1 in 5, 1 in 7. So the only time that is common to all of them actually is today. So what we do is we take all those values in the future and calculate their equivalent today, and we'll see how to do that in the next few slides. So how much is an investment option worth now? And if I have many, which one is best? How much is it worth in the future? What are the true costs of a loan? Again, if I pay something for a loan today and that loan is for 6 months, it's a lot more expensive than if I pay the same amount, but the loan is for 10 years. So I have to be careful with comparing the different costs that I incur in a loan, when do I have to pay them, how much they are, etc. How do I compare different investment opportunities? And I've mentioned that already. So I'll leave that for now. Look at the different costs and the different returns, all of those. Now, why do I ask these questions? Life would be very simple if nothing changed. If I had £100 today, I could do something with those £100 today, which would be the same I could do in 6 months' time, or in a year's time, or in 2 years' time, etc. But you know that's not the case. You know that prices change. You know that returns change, interest rates change, everything changes. And what is the key change behind all of these? As it says in there, it's called inflation. Inflation means that money loses value over time. And if I ask you the question, would you rather have £100 today or £100 in the future? Most of you will hopefully say today. And those of you say that, you are right. Because what happens is, what I can do with £100 today, because of inflation, I want to be able to do a year from now. Because if inflation is, for example, 5%, what I can do with £100 today, I'll need 105 in a year's time. Or if I still only have the £100, I'll be able to do less than what I could do today. So that is the concept of losing value. Don't confuse the fact that if you put money in the bank and the bank gives you an interest, you will have more money. But that's not having more value, it's having more money. So for example, let's say I have £100 and the bank gives me an interest of 5%. Next year, I'll have 105. So I'm going to have more money. Does that mean I'm wealthier? It may not mean that, because let's say for the sake of argument that inflation is 7%. So now I've got £100, I can buy a basket of goods with that £100. In a year's time, with the interest I get from the bank, I will have 105. But because of inflation of 107, to buy the same basket of goods I bought today with £100, I'll need £107. So yes, I'll have more money, 105 versus 100, but to have the same wealth, I need even more. I need 107 instead of 100. So, whereas now, the money I had and the money I needed was the same, in the future, although I have more money, I need even more to be the same. So actually, I am poorer, even though I have more money. So, to get time value of money is not comparing what money I have now with what I have in the future, is comparing either what I can do with the same amount of money, or compare what I need, how much I need to buy the same goods at the different points in time. So whenever there's inflation, money loses value over time. money increases in value over time if there is deflation, which doesn't happen often. So, as I was saying, and I just spoken out of turn in the previous slide, in a world with no interest, life is easy. I buy a car now, I pay 12 months installments of £1,000, which is cheaper? None of them. It's exactly the same, because there is no inflation, there is no interest. So if somebody gives me £12,000 now, or I have to pay £12,000 now, or they give me £1,000 every month, or I have to pay £1,000 every month for the next 12 months, it's exactly the same. But that's not realistic. And as we've just discussed, over time, money loses value in most circumstances. So what I need in the future is going to be more than what I need today. That loss of value, and I've talked about it a little bit already, is compensated by earning interest, by increasing the amount of money that you have. So it reduces in value by what is happening around you, by inflation, by demand for products, by increasing the number of people that are using the same resources, and therefore the price going up, by all of those things. And we counteracted by earning interest, by using the cash that we have and don't spend, and increasing the amount of cash we will have in the future. So products that we buy have a price. Money also has a price. So if we allow other people to use our money, we charge them for that. If we need to use other people's money, they charge us for it. Because, as it says in there, when borrowing, we are buying or leasing an asset. That asset is cash, and we will use that. So, for example, if I need to buy a house and I don't have money, I go to the bank. But I may take 15, 20, 25 years to pay the bank. And for that time period, the bank doesn't have that money. And so they will charge me for the right to use their money over that period of time. So what we have is a business relationship like any other product. A lender will allow a borrower to use his or her capital. The borrower has to pay the price for that benefit, which in this case takes the form of interest. Now, interest can be calculated in different ways. And it is calculated in different ways depending on the terms that are agreed between the borrower and the lender. The two simplest the simplest form of interest is what's called simple interest. The opposite is what's called compound interest. What is the difference between them? And we'll see the calculations in the upcoming slides. The key difference is, with simple interest, the borrower pays the interest as you go along during the life of the loan. And because of that, that interest never accumulates. And therefore, the amount that you owe to the lender is always the same. And because the interest rate will normally be the same, the amount of interest that you pay will also always be the same. So you agree how often the interest is paid. When that moment comes, interest is calculated and it's also paid. And therefore, the amount stays exactly the same, as it says in that second bullet point. only principal remains in debt at the end of the period because you pay the interest. With compound interest, that's not the case. With compound interest, you calculate the interest at the point in time where the calculation was agreed, but the borrower doesn't pay the interest. It simply calculates the interest and increases that amount to the amount already in debt. So by the point in time when the interest is calculated, you will not only owe the principal, the amount that you borrowed, but you will also owe the accrued interest. What that means is when it gets to the next period, if the interest rate is the same, you're going to accrue more interest because you're paying interest on the original principal plus interest on the amount of interest from previous periods that you haven't yet paid. So how do we calculate these? With simple interest, we do a simple calculation. We know the principal, we know the interest rate, and we know how many times we're going to pay. So say, for example, I take out a loan over 2 years and the loan is for £1,000 and the interest is 1% every month. I know it's high, but allows us to do the calculation easily. So £1,000 I borrow, 1% a month. So every month I'm going to calculate 1% of 1,000, which is 10, and pay that. Over the 24 months, the amount that I owe never increases because every month I calculate the £10, I pay the £10. So the calculation that you see in the slide is just the total amount of simple interest that I'm going to pay for this loan. I borrow £1,000. I'm going to pay a total interest of P, the principal 1,000, times I, interest rate 1% per month, times T, in 2 years, 24 months. So 1,000 times 0.01, 10 times 24, 240. So I took out a loan for 2 years for £1,000 at an interest rate of 12% per year or 1% per month. Calculate and pay the interest monthly. So throughout the 2 years, I'm going to pay £240 at £10 every month. So I pay those 240 of interest, and then in 2 years' time, I pay back the loan. The loan principal has never changed. The amount that I owed has never changed, and it cost me £240 of interest to be able to use that £1,000 for 2 years. As another example here, I borrowed £25,000 for 5 years, annual interest of 4%, but in this case, I'm going to pay the interest annually. So I just take £25,000 times the 4%, which is £1,000, and that's what I'm going to pay each year. And because the loan is for 5 years, just multiply that by 5, which is the value of T. So I'm going to pay £5,000. Exactly the same I said before. It cost me £240 at monthly payments of 10. Here it's cost me £5,000 at yearly payments of £1,000. And I always owe the £25,000 throughout the 5 years, which I pay them at the end. So the price that I'm paying for using this £25,000 over this 5-year period is £1,000 a year, or a total of 5,000. That's how simple interest works. Now, as an exercise here, 1,500 is invested for 6 years in a savings account on a building society, which pays simple interest at a rate of 3%. How much will you earn each year? How much will you earn in total? How much will you have accumulated at the end of the 3 years? So very similar calculation to what we just did here, and the solutions are at the end of the notes. My recommendation, pause this recording now, work through this exercise, and then when you get to the end, we'll see. Obviously, if you want to go to the lecture notes and check, fine. Otherwise, when you get to the end, you'll see the solutions. Compound interest works obviously in a different way. And in this case, unlike with simple interest, we don't actually calculate the interest. What we calculate is the amount that is owed. Obviously, we can calculate the interest. So say, for example, I borrow £1,000 at 10% a year. Next year, I will calculate 10% of 1,000 is 100. So I'm going to owe 1,100. 2 years from now, 10% of 1,100 is 110. So I'm going to owe 1,210. 3 years from now, the starting principal is 1,210, so the interest is 121. So at the end of the year, I'm going to owe 1,231. And so 1,210, so 1,331. So I can do this calculation all the time. But there is an easier way, which is the formula that you got in there, where you can calculate at any point in time. So the example I gave, principal in there is 1,000 times 1 plus I, where I is the interest rate of 10%. For the first year would be 1,000 times 1.1, 1,100. Then it would be 1,100 times 1.1, which would be 1,210. Then it would be 1,210 times 1.1, which would be 1,331. And I can keep going, but rather than keep doing these every year, let's say, for example, it's 10 years, then I would simply do 1,000 times 1.1 to the power of 10, and then get the number. Now, in the case of simple interest, because we're always calculating the interest, to calculate the total, I need to take the principal and add the interest. So I got the principal, calculate the interest, total is the sum of the two. Here, calculation is the other way around. I've got the initial, the principal. With these, I calculate the total. So what I do, for example, for the first year, P1000 times 1.1, 1,100. So I started with 1,000, I end with 1,100. So how much is the interest? The difference between the two. So one more time, simple interest, I've got the principal, I calculate the interest, I add them to get the figure at the end. Here, I got the principal, I calculate the figure at the end. By taking one away from the other, I calculate the interest. Okay, so here I need to know the principal, how much I borrowed, I need to know the rate, and I need to know for how many periods. And then I calculate the amount that is due at the end, which includes both the principal and the interest for the whole period of the loan or the investment. So one example of compound interest, using the same example as before, a loan of £25,000 for 5 years, at 4% a year, but in this case I don't pay the interest. So I simply calculate in this case the value at the end, 25,000 times 1 plus 4% to the power of 5, which is £30,416.32. And then if I take one away from the other, that gives me interest of £5,416.32. If you recall from simple interest, the interest that I paid was 5,000. So that means that if I take out a loan with simple interest, I pay 5,000. If I take out a sim loan, that is same principal, same duration of, in this case, 5 years, same interest rate, it cost me £5,416.32. So that difference of £416.32, what is it? Easy. It's the interest on interest. So interest that was accrued but not paid, in subsequent periods, it's also charged interest. So I'm paying another £416.32 of interest on interest that was accrued previously but not paid. And that's the difference. That's why if it's a loan, we'd rather take it on simple interest because we paid less. If it's an investment, we'd rather get paid compound interest because the amount we invest becomes a bigger amount in the future. Now, one very important part of any financial calculations, and if you do any further finance studies in the future, once you develop your career and get promoted to a point where you'll become a very senior manager, and you may want to know some more finance. In this calculation before, we multiplied by 1 plus I, where I is the interest rate, to the power of t, which is the number of periods. That is called the compounding factor. It's what we apply to the principal to calculate the compounded amount in the future. So what that allows us to do is to transform a present value into a future value. But sometimes we may know the future value but not know the present value. So say, for example, I'm trying to keep money aside to buy a car in 5 years' time, and I know the model of car I want, and it's going to cost me £25,000. So I know that future value. I know the interest rate I can earn if I put the money in a savings account. So I need to decide how much money am I going to put in that savings account now. So in that case, I need to take the future value and calculate the equivalent present value. Instead of compounding from today to the future, what I'm now going to do is the opposite. And that opposite is called discounting from the future to the present. So in that case, as you can see in that third bullet point, what I do is I take the future value and I apply a discount factor. And that discount factor is very similar to the compound factor, but instead of multiplying, I'm going to divide by 1 plus I to the power of t. So the discount factor as a whole is 1 over 1 plus I to the power of t, which I can then apply to the future value. So in the previous example, for example, if I simplify and I take a 10% rate for 1 year, to go from the present value to the future value, I take £1,000, multiply by 1.1, give you £1,100. But if I start with £1,100 in the future, I'm going to multiply it by 1 over 1 plus I to the power of t, in that case 1 over 1.1, and that will give me the £1,000 today. So in situations that I need to take a present value and calculate a future value, I use a compound factor. When I've got a future value that I need to apply to calculate, a present value, I apply the discount factor. Again, a practice exercise, similar, 1,500 invested in that same savings account at the same 3%, but in this case using compound interest. Again, I recommend you pause this recording, go do this calculation, and then at the end we've got the solutions for this. Now, as I've just mentioned, we can have a compound factor and a discount factor. Those are used for two very important processes in finance, which are the process of discounting and the process of compounding. That's why we use a discounting and a compounding factor. When discounting, we are taking a future value and calculating the equivalent in the present. When compounding, we are taking a present value and calculating the equivalent in the future. And some very similar example to what I just gave you. Normally, we try to use simple examples because they are the easiest to visualize. I used with £1,000, here with 100. Value today of £110 received next year. You take the £110, multiply by 1 over 1.1. And that gives you £100 today. Value next year of £100 received today. If I can invest it at 10%, will be 100 times 1.1, which is £110. When compounding and discounting, as we went through, we are using a rate, a discount rate or a compound rate. And that rate is something that we see in the market when we go to the bank, when we have investments we want to make, or when we have loans that we need to take out. It's called the interest rate. Interest is what you earn or what you pay on cash that you borrow or that you invest. And so we calculate the interest rate, which is the rate at which interest is calculated. Now, one important distinction, and something that catches out a lot of people when they go to the bank, is the distinction between nominal rate and effective rate. The nominal rate is the one that is quoted, but in many situations it's not the effective rate that you pay or earn. And the reason for that is that there is compounding taking place at different points in time, at different regular intervals. Normally when interest rates are quoted, they are quoted as annual rates. So you go to the bank and the bank will tell you 5.9% or 7.5% or anything like that, which is an annual rate. But for example, if I take out a loan in a bank that tells me 7.5% and charges me interest every 6 months, and I go to another bank that also tells me that they charge me 7.5%, but they charge interest every month, the second one is charging me a lot more. Because, if you recall the explanation we went through earlier, when the interest is calculated every month, when it gets to the second month, I'm going to pay interest on the interest of the first. When it gets to the third month, I'm going to pay interest to the interest of the first and the second. But if it's charged every 6 months, I pay no interest on anything other than the principal until that 6 months point in time. So we need to be very mindful when we are comparing rates, when we are assessing the cost of loans or the return on investments with the quoted rates. We need to be very mindful of what is the actual cost or the actual return. And in order to do that, we need to know the frequency with which interest is calculated, that is, either paid or earned. Also, a lot of loans, they have some fees, and the fees may be added to the principal, and therefore interest is going to be charged not on the amount you actually borrowed, but on fees that were added on top. So you borrow £10,000, but there is a 2.5% fee, arrangement fee on the loan. So rather than pay interest on £10,000, you're going to pay interest on £10,250, which is the additional 2.5%. So you got to be very mindful of the actual calculation. So as it says in there, nominal is the rate that is quoted, the number that is used for the calculation. But if either the rate is calculated more than once in the period, or if the interest is not paid at the end of the period, the interest is going to be more, because it's not a simple interest calculation, it becomes a compound interest calculation. So the effective rate is something that needs to be calculated, taking into consideration those adjustments. And when comparing different loans from different banks, or the returns on different investments with different banks, we need to compare effective rates, not nominal rates. There may be situations where, for example, in a loan, one quotes a higher rate, but it turns out to actually be a cheaper loan because the frequency of the calculation of interest in the one with a lower rate is a lot higher, and that makes the effective rate actually higher. So all this happens because the compounding period is not restricted to 1 year. It can be calculated half yearly, quarterly, hourly, or even something that's called continuously, where instead of using the formula that we've been using for discounting and compounding, we actually have to use the formula for exponential. And if you have an interest on that, have a look in the references and that will be explained there as well. So let's have an example here. Take out a loan of £200, or not a loan, sorry, in this case an investment for 8.25 years, and one pays you 3% per half year, the other one pays you 2% per quarter. Now, quoting it this way, it seems that the 3% is more, but actually in one period where you get 3% in the first case, you get 2 periods of 2%. So you're effectively getting more, and that's what you see in the result. Also, in this case, if we are investing for 8.25 years, if we invest at the 3% per half year, we're going to get interest up to the end of year 8. And then we have 3 months, the last quarter of our investment, where we're not going to earn any interest, because we would only qualify for interest if we left the money there for 6 months, not 3 months. Whereas in the second investment, we do get interest right until the end, because we get paid interest quarterly. So in the first case, the 3% per half year, we only get paid interest 16 times, because there are 16 half years in 8 years. But in the second case, we get interest for 33 quarters, because there are 32 quarters in 8 years, and then the additional quarter of a year. So you can see that there's a very significant difference where we get £120.94 of interest in the first investment, but we get 184.45, an additional £64 or 50%, over 50% more of interest. So how do we calculate this effective rate? As I said, we need to compare like for like. And in order to do that, we're going to calculate the effective rate per year. So when we have 3% per half year or 2% per quarter, we're going to need to compare it with the same period. Now, we can't compare every quarter because in the first case, we don't get interest every quarter, so that would be wrong. The first rate, the 3% per half year, does not have a comparable quarterly rate. We could calculate the effective rate for every half a year because both rates, the 3% per half year and the 2% per quarter, they both pay interest at the end of each half a year. But the best way is always to compare at the end of the year, that is with an annual rate. And so the way to do that is to use the formula that we've got in there, where I represents the effective rate, R represents the nominal rate, the nominal annual rate, and X represents the number of compounding periods in a year. So what does that mean? Using the example from the previous slide, 3% per half year is the same in nominal terms as 6% per year. So to use that formula, we would do 1 plus 6% over 2, because there are 2 half years in a year, 2 compounding periods, which effectively is 1 plus 0.03, and then do the power of 2 because of the 2 compounding periods. If we then take away 1, that gives us the interest rate in decimal form. If we multiply by 100, that gives us the rate we want. If we were using the other one, same thing, 2% per quarter, nominal, is the same as 8% per year, nominal. So we would use their formula and do 1 plus 8% over 4, because there are 4 compounding periods of quarters in a year, and then, which effectively is 1.02, and then to the power of 4 again. What we would find, even if the rates were the same, for example, if they were both 6% per year, we would find that the one that is compounded the most will give a higher effective rate. Okay, so I mentioned in the previous slide, the compounding period can be half year, quarter, months, etc., and it can be continuous compounding. And I mentioned that we would use exponential formula in that case, and you can have a look. And in this case, just to calculate the effective rate, we would do E, which is again the letter E that represents a constant, to the power of R, where R is the nominal annual rate, minus 1. What I just explained over in the previous slide. So the 6% compounded half yearly rate. So 6%, notice there the letters PA, per annum. So nominal rate of 6% per annum compounded half yearly, and 8% per annum compounded quarterly, which is the example from 2 slides ago. So to calculate the effective rate, we do 1 plus 0.06 over 2, which gives us the half yearly 3% to the power of 2 minus 1. And to calculate the effective rate of 8% compounded quarterly, 1 plus 0.08 over 4, which is the 1.02 to the power of 4 minus 1. And you can see, as we saw in the calculation of the amount at the end of the year, that the quarterly rate of 2% is significantly more than the half-yearly rate of 3%. Here is another exercise. Again, the solution is going to be at the end of these notes, and we'll have a brief discussion when we get there. As I did before, advise take a little break, try to calculate it. Two different questions. One, investing 5,000 for 5 years in a deposit that pays 8% per annum compounded quarterly, rate that we've been looking at, and then investing 1,000 and for 3 years, and here you've got 6%, 3% per half year, which effectively is 6% per year nominal, or 6% per annum compounded quarterly. So here the nominal rate is actually the same, 6% and 6%, and the first case 2A is compounded half yearly, in the case 2B is compounded quarterly. So the only difference is in the period of compounding. Now, as well as calculated, and even before you calculate it, think to yourself which one is going to be the one that's going to give you a higher value of your investment at the end of the 3 years. We've gone through that in the previous slide, so you should hopefully be able to answer that question correctly by now. But think to yourself, do you think you're going to get a bigger value in A or in B? And then calculate it, and then go back to the end and compare the results with what you've got. Now, so far, we've been looking at making a payment. So make an investment now, collect it in the future, take out a loan now, pay it in the future, or pay interest as we go along and pay the principal at the end of the loan in the future. But that happens in a lot of instances. Most business loans are like that. So banks will lend money to a bank for 5 years, and they will be paid interest throughout and the principal at the end. And it's also used a lot of times on personal loans. But when especially individuals take out very large loans, two things happen. The reason why we take out very large loans is because we don't have the funds available for normally a purchase we're going to make. And that purchase is of a big asset, like a house, potentially a car, potentially a loan to start a business. But in most cases, the most common is going to be a mortgage, a loan to buy a house. Also, throughout our careers, we need to save money in order to be able to retire at some point and still have an income on which to live on. So we're going to be making payments into some form of investment such that at retirement we can collect money enough to generate an income for the remaining years of our lives. Both of those instances, we have a series of payments, or as it says in the slide, regular payments. In the first case, take out a loan, which is a big lump sum of money, and pay it over time. The second case, make payments into some form of pot where we are throwing money at, so that at the end we've got a big lump sum of money. Now, in both cases, what is happening is, because the period of time is very large, the risk is very high, especially for the entity that doesn't have the money. So in the case of the retirement fund, the pension fund, the risk is with us paying, because we are putting money into the pension pot, and then suddenly we may die and we lose all that money. Or suddenly interest rates may change and we have a lot less than we expect, and we're going to have to make bigger payments. In the case of a loan, the risk is with the lender, because they've given us the money, we've bought the house, and unless we are able to generate enough cash to pay that big lump sum at the end, the bank, the lender, is going to be in trouble. And so they do not want to take that risk. And in order to minimize that risk, they force us not just to pay interest, but to repay the loan over time as well. So what are these regular payments? Both examples we've got in there: mortgages, other loans, pensions or pension fund, life insurance, etc. And they are characterized by having one point in time when there's a lump sum. Either we take a loan now as a lump sum, or we're going to collect at the end as a lump sum. And in the case of a loan, we've got a lump sum followed by a series of payments. In the case of a pension, we've got a series of payments followed by the lump sum. What characterizes those series of payments is those three things that says in the slide. They are a fixed amount, so it may be every month, it may be every quarter, it may be every half year, whatever it is. Most cases it's every month. We pay the same amount. We pay at a specified time period at equal intervals. So first day of every month, for example, that's the case with my mortgage. I pay it on the first day of every month. And the interest rate is fixed. Now, in a lot of cases, the interest rate may be variable, but when there's a change, there's a recalculation of the payment. And then it's from then on until there's another change in the future, the rate remains the same. Now, we can calculate regular payments in the same way we've calculated individual payments. But imagine a mortgage for 20 years, paid monthly, that's 240 payments. So we would have to be discounting 240 payments to today to find how much we can afford. Or if we take the lump sum, we would have to calculate a value such that 240 payments discounted to today will be equivalent to it. So it will be very time consuming, very intensive work to do, and unnecessary, because when we have regular payments, we can simplify the calculation. The first thing we need to understand is what type of a regular payment we have. So the first type I mentioned, when we take out a loan, for example, we have the principal now, the lump sum, and we're then going to pay it over time. So when we discount all the payments we're going to make to today, it should be the same amount. So we have a situation where we are discounting all the future payments to today. Because of that, we are used, as you see in there, the discount factor that we saw earlier. So that's what's going to happen. That type of regular payment, it's called an annuity. The second case where we are going to build a pot to collect an amount at the end. We are going to deposit that money, earn interest or other return on it, and we are going to keep compounding all those payments plus the return to generate a lump sum at the end. So in this case, we are compounding, and as we saw before, we use the compound factor of 1 plus I to the power of t, where t is the number of periods the payment remains in situ. This type of regular payment is called, as it says in there, a sinking fund. We are sinking funds into that pot to generate a future amount. So then the question is, how do we calculate it? I said we could simplify it. And without going into the mathematical explanation of it, for those who are interested, just a few words. The principle of these is calculating the sum of the first n terms of a series, of a geometric series. And so that's what it says there. Sn represents the sum of the first n terms of the geometric series. But we don't need to know that. All you need to know is the formula that is in there. And that formula says that the value, which may be today's value if we are discounting, or it may be the future value if we are compounding, is equal to A, which is the common factor or constant, which is the payment effectively that we are making or receiving, multiplied by 1 minus r to the power of n, where n is the number of payments, divided by 1 minus r. Now r represents, as it says in there, the common ratio. And the common ratio, if we are discounting cash flows, is 1 over 1 plus I. If we are compounding, is 1 plus I. So for an annuity, that formula becomes A times 1 minus 1 over 1 plus I to the power of n over 1 minus 1 over 1 plus I. If we are compounding, calculating the future value of a sinking fund, that formula becomes A times 1 minus 1 plus I to the power of n over 1 minus 1 plus I, which actually can be simplified as simply I in the denominator, because you're doing 1 minus 1 plus I. So it simply becomes I, or minus I to be more precise. Okay, so that's the formula that we can use. Now, there is a little trick that you have just to be aware that in an annuity, the first payment can take place either immediately or at the end of the first period. If it takes place immediately, don't need to adjust, just use that formula. But if it just takes place one period from now, which is the most common situation, you divide by 1 plus I. In a sinking fund, normally you make the final payment and you collect the lump sum straight away. So for example, you make the final payment into your pension fund on the last months, and then you collect the lump sum so that you can invest or do whatever you want with it. In that case, you need to do nothing. But if you make the final payment and then wait one more period to collect the lump sum, then you multiply the total value by 1 plus I. So calculate the formula, multiply the formula by 1 plus I. Here's another exercise, and we'll go through it at the end. Again, as in previous cases, I recommend you might stop here, try to solve it by using the formula, and then we'll go through it at the end. So in this case, we are calculating an annuity, it says in there, of 5,000, starting at the end of year 1 and continuing for 12 years altogether. Discount rate 10%. So this is a case of we're going to pay today to receive £5,000 a year for the next 12 years starting next year. So stop, try to solve it, and then we'll go through it in a few minutes. Now, one other important topic of financial maths, and it's actually the most important topic in a lot of cases for businesses, is the issue of investment appraisal. Why is that so important? Because investments involve large amounts of money, involve a significant commitment. What is an investment? Something that a business will do that will last for a long time in most cases. It's not something that you do like buying some stock to resell. It's not something like pay the salaries of the employees, where you have an expense and that's it. An investment, you are committing funds in most cases for the long term. So you're building a factory. It's going to take you time to plan for the factory, then to build the factory, to buy the equipment for the factory, and after a long period, normally various years, you have a factory that you can use. Now, if you built that factory to build products, to make products that the market wants, that's great. You've made the investment, you're going to get the returns through the sales of the products. But if it turns out that the products you were planning to sell the market doesn't want, you're in trouble, because now you've committed all these funds. In a lot of cases, you borrowed those funds and you're going to have to pay them back, but you're not going to generate any revenue from it if the market doesn't want your products. So you're in trouble. And that's why it's very important before you make an investment that you appraise it very well. So as it says in there, it's a significant commitment of resources, large amount of cash involved, long-term implications, because you're committing to build something or invest in something or open a subsidiary in another country and hire staff, etc. So there's a long-term implication on all of that, and because of all of that, there's significant risk attached to it. Because of that, as I said, we need to appraise investments. How are we going to do it? There are various different ways, and I'm not going to go into the detail of all of them, but just to simplify, there are 4 main methods that companies use, and they are generally used by every single company. Not all 4 of them. Most companies will prefer one or the others, one over others, or a couple of them. So for example, I used to work in a company that used mostly payback period and net present value, but other companies prefer others. Key thing with these 4 methods, the names are in there, you can read through them, is that the first 2, the accounting rate of return and payback period, are what's called non-discount methods. What that means is that we take the cash flows, or in the case of the accounting rate of return, we take the profits, and we don't compare them with their equivalents at the same point in time. We use them as are. So for example, payback period, it's how long it takes to recover the investment. If we invest 10 million and we get 5 million next year, 2 million the year after, 3 million the year after, that means it took us 3 years to recover the 10 million, and the payback period is 3 years. Now, the reality is the 3 million that we're going to receive, or the 2 million we're going to receive in 3 years' time, is worth a lot less today, but the payback period doesn't take that into consideration. That's why they are non-discount methods, because they do not discount cash flows to today, which the other two, the net present value and the IRR, do. So we don't use the cash flows as they are, or called the nominal cash flows. We use the discounted cash flows for comparison purposes. Now, when we use the models, the methods for appraising the investments, there are two types of decisions that we are making. One, we can simply have an opportunity and assess it, and therefore decide whether to go ahead with it or not. That's one type of decision. But in companies, in real life, the majority of times there are many investment opportunities. So you can build a factory, or spend more money developing new products, or invest in a foreign subsidiary, or acquire another company that has a complementary product to yours. Lots of different things you can do. And in that case, if you do not have the financial resources to do them all the good ones, you have to select. And that's the second type of decision, which is compare the assessment that you made of the quality of the investments and choose which one or which ones to go ahead with. Now, this slide just gives very briefly the formulas for all the methods. Again, I revert you back to the references if you want to learn in more detail of these methods of assessing the quality of an investment. So very briefly, ARR, you just take the average profit, which will be the profits that you make over the life of the investment, and add them all together and divide by the number of years. And then you divide that by the average investment. And the average investment, you can do it with adding the initial investment and the scrap value. Scrap value is the value that an investment will have at the end of its life. So say, for example, you buy a piece of equipment, you use it for 5 years in your investment, and then at the end, you can still sell it for a certain amount of money. So you buy it for 10 million and you can sell it for 500,000. So you just take the 10 million of investment plus the 500,000 of scrap value, 10.5 million divide by 2, and that will give you the average investment of 5.25 million. When you calculate the IRR, then to decide, you compare the IRR with the minimum required return that the company decides on based on its cost of capital. The payback period, as I explained in the previous slide, is just how long it takes to recover the investment that you made in terms of the number of years that it takes. The net present value is a method where you add the present values of every cash flow. So say an investment for 5 years, you can see in there t equal to 1 up to 5, and so you divide you calculate the present value of the cash flow in year 1 by dividing by 1 plus the discount rate to the power of 1 plus the present value of the cash flow in year 2, and in 3 and in 4 and in 5, add them all together and take away the initial investment. The decision method in this case is, if it's positive, it means that the present value of the future cash flows that you generate is more than the initial investment, so you should go ahead. But if it is negative, it means that the present value of all the future cash flows is less than the initial investment, so you shouldn't do it. The IRR uses the same formulation of the NPV, but instead of calculating the value today, what it does is calculates what return we are getting. So what it does is makes the equivalent to the NPV equal to 0, and the cash flows, we know them. So it calculates the interest rate or discount rate that makes the present value of all the cash flows exactly the same as the initial investment. So take, for example, let's say a company's cost of capital is 15%, so we calculate the net present value of an investment for 5 years, and it comes out as 1.5 million. So that means we should go ahead with the investment because it generates more value than what we spend now. But what return we actually getting, we don't know, because we know we're getting 15%, which was the discount rate we use, plus something more. So by calculating the IRR, we know exactly how much return we are getting, because what we do is, instead of making the NPV equal to 1.5 million, we make it equal to 0 and see the discount rate that makes that true, which in this case is going to be a higher discount rate, say for example 22%. If we replace I with 22%, we get a net present value of 0, and that means that the return we are actually getting on this investment is 22%. Okay, so with that we completed the material, and now there is one more exercise, which is to do with investment appraisal. An investment for 5 years, we invest 1 million now, scrap value is 50,000, and that investment will give us cash flows of 250, 400, 350 and 300,000 in the next 5 years. If the discount rate, the cost of capital for the business is 8%, using the 4 methods, assess that investment. So that's all for this topic. Now very quickly, I'm just going to go through the solutions for the exercises. This is the one from slide 12, where you were asked to calculate the amount of interest paid for one payment, for the total, and then the amount of interest, the total amount of that is generated. So can't recall, to be honest, if it's an investment or a loan, but I suspect it's an investment. I invest 1,500. I'm going to get 45 each period. Because I invest for 6 periods, that's 270 altogether. So at the end, I will have 1,500, which was the investment, plus 270 of the interest. The second case was similar, but with compounding. And you'll see that in this case, we are getting significantly more. So, and you saw at the time when we went through the slides, I said we can calculate one by one, because we just keep calculating the interest and multiplying it again. And so in this case, we've got £238.91 of interest instead of the 200 and the 170, sorry. Okay. The next question was in slide 22, which was calculate the future value if I invest 5,000 now at 8% compounded quarterly for 5 years, then how much money have I accumulated? In this case, you can see If you recall at the time in the slides, I said that with simple interest, we calculate the interest, and then to calculate the full amount, we add the two elements together, the principal and the interest. And then I said that when we use compound interest, that's not what we do. We calculate the future amount, in this case 742974, and then if we want to know the amount of interest, we need to take away the principal, in this case 5,000, so the amount of interest would be 2,429.74. Then we had the other example, which was to illustrate the fact that even when the nominal rate is the same, in this example 6% per year, if the compounding is more frequent, that leads to a higher amount of interest. And I think I've said in an earlier slide, a good thing if you're making an investment, not such a good thing if you're taking out a loan. So in this case, because the amount is small, only £1,000, and it's only 3 years, the difference is not very big, but it's still an extra £1.57. The other thing that we calculated at that point was the effective rate. And you can see that even though the nominal rate was 6%, and that would be what the bank would advertise, whether it is on a loan or in an investment, but effectively the rate of interest that is being paid or received is 6.136% per year. Now, you've got to be very mindful for you as individuals when banks advertise rates. Make sure you know very well the compounding period. Make sure you know if there are any fees or anything else, because banks on loans will try to list a rate that is as low as possible to attract borrowers, but then charge a lot more potentially. Now, this example from slide 27 was a case of a regular payment. And if you recall, it was a regular payment of £3,000 at 10% for 12 years. And the question is, how much should I pay now to be entitled to receive £3,000 every year for 12 years at a discount rate of 10%. Now, the value you've got in there is calculated as 3,000 over 1 plus 1. If you recall, because the first payment is not now, it's in one period, we discount by 1.1, 1 plus the discount rate, and then we multiply that by the formula of the sum of the first n terms of a geometric progression, which is 1 minus 1 over 1 plus the rate to the power of n divided by 1 minus 1 over 1 plus the rate. And so that says that if I want to receive £3,000 for 12 years starting next year, if I can invest my money now at 10% per annum, I will need to invest now 20,441.08. Now the question is this a lot? Is this too little? Have I done the calculation right? So there's a relatively simple way to have a quick test of whether you did it right or not. Now, if it is 12 payments of £3,000, 12 times 3 is 36. So I'm going to receive £36,000 in total. Now, if I'm paying it now and earning interest on it, I would always have to be paying less than what I'm going to receive. So 24,441.08 is less than 36,000. So this is in the right direction. Then the question is it a lot or is it a little? Because as you can see, if I'm going to get 36 and I'm paying 20,400, I'm going to earn a total of 15,600, give or take, of interest, which is quite a lot. It's almost as much as I have. Now, then, whether that is right or wrong depends on two things. How long am I going to have the money invested for? And what is the rate, the interest rate? So here the question is, I'm going to get the first payment next year. So one part of my money is only going to be invested for a year. But the last payment is only going to be 13 years from now. So on average, I'm going to have money invested for 6 years. Small amount for 1, then some for 2, then some for 3, all the way up to 12. So roughly, on average, about 6. The interest rate is 10%. 10% is quite a high rate. 10% over 6 years is 60%. If it's simple interest, because it's compounded, it's even more. So £15,000, give or take, that I'm going to get of interest is about 75% of what I invest. If you think about it, 10% a year compounded for 6 years on average can be roughly 75%. So that gives you a good idea that you've done the right calculation and that value is correct. Now, this is not scientific, but this is always just to give you, I like to have this discussion just to give you an idea of how to be comfortable with numbers. Okay, so that's the formulation, and the answer to the question is, in order to be able to receive £3,000 a year for 12 years starting next year, I need to invest now £20,441.08. The final exercise, I didn't put it here, but there is an Excel file next to this recording as well, and have a look at that Excel file. What I've done in there is I've put the solution there, but rather than just give you the numbers, it's all based on the formulas, so you can follow the formulas comparing with the slide of the respective calculations and formulas that is earlier in this pack. Okay, so try to do it on your own based on the formulas and then check with that Excel file. And so for the last time, because this is session 5 of 5, there's some references, and have a look at the exercises, at the books, the sources, which contain a lot of exercises and the explanation. Bear in mind that sometimes there are differences in terminology, even within English book, American English versus English. The last book that I've got in there is a book that I think it's very good, but it is an American book, so terminology sometimes is a little bit different, but it's actually good for you to look at both and be able to see the differences. So I hope you enjoyed this topic. I hope it caught your interest to study more on these, the same with the previous 4 topics, and I hope you enjoy the degree you're doing here with the university, and I wish you a very long and happy and prosperous life.